In this third video on elliptic curves, we're going to talk about a slight detail that we had been brushing over in the previous videos to get ourselves entirely equipped to create Keeley tables for elliptic curves, knowing that they form a group. So the slight point that we've been brushing over is this point that we really need to have a binary operation on our elliptic curve. And we talked about how to combine an element with its reflection across the x-axis. That was initially problematic for us in the first video. And so we added this point infinity to remedy that. But one slight point that we did not discuss in that first video is, what if I happen to try to combine a point with itself, and I want to try and draw a line through a point in itself and one other point on this elliptic curve? How am I going to accomplish this? So in the previous video, I just want to review what the process was for combining distinct points on the elliptic curve, because we're going to use that process and modify it some in order to learn how to define our binary operation on a point along with itself. So in that previous video, we were working with the example y squared is x cubed minus x plus 1, and we were working modulo 5, and we had done an example in that video computing 0, 1.14. So let's just recall what the points on that elliptic curve were. So what we did in order to compute 0, 1 dotted with 1, 4 is we found the slope of the line connecting those 2 points with a change in y over a change in x, and we found that that slope was 3. And what we would do is list out all of the points on the line that connects 0, 1 to 1, 4. And I put line in quotation marks there because when you plot everything modulo 5, it's not going to look like a straight line, but it's still following that concept of what it means to be a line. So we would start at 0, 1, and the next point on the curve would be over 1 and up 3 units, so it would be 1, 4. So it's a line going through 0, 1, and 1, 4. After that, we would go over 1 unit to the right and up by 3, and so on. So when we go from 2, 2 to 3, 0, we're going over 1 and up by 3, but we're modding each time by 5. Modding 5 by 5, we get 0, and that gives us this collection of points right here. And then what we did is we said these 2 points we know are on the curve. The point 2, 2 is not in my list of e-values here. The point 3, 0 is, and so that is the third intersection point. Those 3 points that lie on the line also lie on the elliptic curve. And so I take 0, 1, and 1, 4 and combine them with the dot operation by taking this third intersection point and reflecting it across the x-axis. And it just so happened in this example that the reflection of 3, 0 across the x-axis is itself. So we didn't actually have any reflecting to do. We'll fix that problem as well with our next example. So the very last example I want to do is figure out how are we going to combine a point with itself. We're going to use the same elliptic curve, and we're going to continue working mod 5, so all of our points are the same. And this time we're going to combine 4, 1 with itself. And shockingly, the answer is we're going to steal this idea from calculus, which is to use the tangent line that goes through the point 4, 1 for this particular curve, because we aren't able to do a change in y over change in x here. So in order to find the equation of the tangent line, we're going to have to use implicit differentiation. So we take the derivative of the y squared part, and we get 2y dy dx, and the derivative of the right-hand side of our elliptic curve becomes 3x squared minus 1. And that equation is valid for all points x and y that live in the elliptic curve, all the values on that previous slide. We are particularly interested in the slope of the elliptic curve at the point 4, 1. So we plug in the 4 value for x and the 1 value for y, and that gives us this particular equation. 2 dy dx is congruent to 1 modulo 5. So what we need to do is now solve for dy dx. Remember that we don't divide by 2. That will give us, a slope of 1/2, which is meaningless to us in this context. So we want to remember to interpret this equation 2 dy dx is congruent to 1 modulo 5. So what we're going to do instead of dividing by 2 is we're going to think about what is the multiplicative inverse of 2 modulo 5, which happens to be 3. 3 times 2 is 6, and that's congruent to 1 modulo 5. So in multiplying both sides of this congruence, 2 dy dx is congruent to 1 mod 5 by 3, we'll end up with a coefficient that is congruent to 1 on the left-hand side. So we'll just have our dy dx over here on the left-hand side, and we'll have a 1 times 3 over here on the right-hand side. And altogether, our slope for the tangent line of the elliptic curve at this particular point 4, 1 is 3. Once we've done that calculus and we know that the slope of the line that we're looking for is 3, we do exactly the same process as we did when we had distinct points. Namely, we start at the point 4, 1, and we move over 1 unit and up 3 units. 3 for this dy dx here. And we continue doing that until we've listed all of the points in space that lie on this line, and line in quotation marks. And we say, okay, 4, 1 was the first one that belongs to E. Here we get incredibly lucky because the very next point that we encounter, 0, 4, also happens to belong to the elliptic curve, while these other points do not belong to the elliptic curve. So we're thinking about this as point A, point B, and this being the third intersection point, point C. And so this is the third intersection point. In order to figure out what 4, 1 dot 4, 1 is, we need to take that point and reflect it across the x-axis. And so we get the point 0, 1 here. So in summary, if we want to create a Cayley table for an elliptic curve modulo some particular prime, the very first step is to find all of the points that lie on that curve and know how to combine distinct points on that elliptic curve, which are things done in the second video. If we want to combine an element with itself, we're going to use calculus and the idea of multiplicative inverses to solve that congruence for dy dx in order to get a slope. And then the process of determining what the line is and what the third intersection point is exactly the same as the distinct case covered in more detail in video 2. And the final point is just a reminder, when you're filling out a Cayley table and you think you've got so much to do on this elliptic curve, remember that we have a couple of things working for us. First of all, the set of points on an elliptic curve forms an abelian group, and so you only have to fill out that upper diagonal of the Cayley table. And second, remember that once you have 3 points that are collinear on an elliptic curve, you can use the fact that that actually fills out exactly 3 values in the upper part of your Cayley table. You'll have a dot b is negative c, a dot b is negative b, and b dot c is negative a when a, b, and c are collinear. And so even though it's a lot of work to find the slopes of these lines and those intersection points, you're really filling in a good deal of the Cayley table each time you do that. So don't lose heart. It's a really important process with fantastically interesting applications, and you can do it.